Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to just give some examples of how to use the thin lens equation combined with ray diagrams in order to predict what the image will look like for a various lens. And what we're going to do here is we're going to go through two examples in one here. So I've got a picture of this lens sitting right here, and this is kind of the shorthand for a converging lens with these arrows pointing outward. This lens, we're going to assume, has a focal length of positive 15 centimeters, and I have placed an object at roughly 30 centimeters from the lens. And what we're going to do is we're going to try to calculate Q, the image distance, and then M, the magnification of the image. When we're done with that, we are going to change that lens to a diverging lens, which has a negative focal length, and repeat the problem. So we're going to try to kill two birds with one stone here. All right, so the first thing you typically do when you're doing an optics problem is you set up a picture. Now this axis right down the middle here has a special name that's called the principal axis. You put your lens in, or mirror, or whatever you're dealing with. Again, a converging lens usually is represented by this double arrow thing with the arrows outward. You put your focal points in. These lenses have two of them. They work in both directions. Now, if you're just, depending on how much time and instrument and tools you have, if you can do this exactly to scale, that's perfectly fine. The intention here is I'm just going to eyeball this. So the actual picture may vary from results slightly. I'll try to get it as close as we can. One thing to keep in mind is that the ray diagrams can sometimes be very susceptible to small changes. So sometimes you can do ray diagrams by hand and they work out all right. Sometimes not. Sometimes the ray diagrams they can kind of come apart in a hurry, particularly when you have things like this object getting close to the focal lengths and stuff like that. So the first thing I'm going to do is start with a ray diagram. And we always draw what are called principal rays. And the first principal ray that I always draw is the parallel one. So again, here's our object, right here. And you typically draw rays coming from the tip of the object. And the first thing we do is we draw the parallel ray. And let's see here. Let's use blue for our rays. Why not? Blue's a nice, happy color. So here's a ray that comes in parallel. And parallel light will be refracted by this lens in such a way that it goes through the focal point. And that's really the point of that lens. All right, so that ray is going to move off in this direction. Right? Next principal ray. A ray that leaves this point and goes through the center of the lens will basically just keep right on trucking. Right? And hopefully you've seen my, whoops, that's off a little bit. I'm going to take the time here to actually change that. Need that point to go right through the center because the ray diagrams are very susceptible to small changes. So a ray that goes through the center just basically keeps on going. That's good. All right, now you'll notice already I can determine where these rays are crossing. Oops, I can draw that better. These rays are crossing here, but I want to take a little bit of time here and talk about the third principal ray. Now these focal point ones, like this one that comes parallel and then through the focal point, they basically work in reverse. A ray that goes through the focal point first comes out parallel. So the way I can use that fact to draw my third ray would look like this. All right, so now I'm drawing a ray that goes through the focal point first. And then that ray will come out parallel. Okay, and again, I got to get it applied right there. And you can see already that my diagram must have got screwed up a little bit. Very likely what's happening here is that, again, I eyeballed this focal length right here, so I put it in the center. Same thing here. Had I measured these and got them right at 15 centimeters, I'm pretty confident that ray would have went right through that point. So what I'm going to do here is I'm just going to approximate it like it does. All right, boom. And again, one of the points I tried to make earlier is that your ray diagrams can be extremely sensitive to small aberrations here. So I did not actually measure this as a 15 centimeter. I just eyeballed it, put it in the middle. Same thing here. Had I measured those perfectly and got them at 15, that ray would go right through that point. But this is good enough for now. Again, the purpose of your ray diagram is usually just to give you a pretty good idea of what's going on. So I now have enough to draw my image. No doubt my image is sitting over here somewhere. Looks about like this. There. Now, before we actually do any calculations here, I'm going to talk about the image. Well, the first thing I notice is it's inverted. Well, actually, let me back up. The very first thing I notice is that's a real image. It is very important that you be able to tell the difference between a real image and a virtual image. This is real because these light rays are actually here. They cross here. And this image is being formed by real rays as opposed to backtrack rays, or what are basically figment of your imagination here. So these are actual light rays here. Therefore, this is a real image. Next, I can see that it's inverted, so I'm expecting a magnification of about or something negative. It looks like it's roughly the size of the first one, so the magnification is probably right around -1. Inverted, roughly the same size. The Q, looks like it's roughly the same distance here, maybe a little bit more. It's real, so I'm expecting a positive value for Q. So the expectations here when we work this problem is a positive value for Q, not because it's on the right, but because the image is real. And then a negative value for M because it's inverted. So there's my image. Now we're going to go through and actually calculate where it's at. So thin lens equation, 1 over P plus 1 over Q equals 1 over F. In this problem, the P is positive 30 centimeters. The Q, we're going to calculate in a moment, and the F is positive 15 centimeters. Now, I know when you look over here to the right and you see this -15, that's because in the next example, we're going to work exactly the same problem with a negative focal length. So this is for another example. So what I'm going to do here is just kind of hang out while one of my helpers calculates a value for Q. Hunter, do you have that yet? 0.3. Okay, so Q, I'm just going to leave this in centimeters. You did that in meters, correct? Okay, so Q came out to be positive 30 centimeters, which is about, means that this distance and this distance are the same. And in my picture, they look roughly the same, so I buy that. Okay, now magnification. Magnification is minus Q over P. That's going to be minus 30 centimeters over P, which is positive 30 centimeters, and we get a magnification of about -1. Or not about, we calculate a magnification of identically -1. So that's very consistent with our expectations for this problem. Right? So now what I'm going to do here is I'm going to take a moment, pause this, clean it up, and set it up for example number 2. All right, folks, I'm back, cleaned up the picture a little bit. What we're going to do now is we're going to work basically exactly the same problem, the same object distance, except now we're going to imagine replacing this lens with a focal length of -15 centimeters. So the first thing I got to do is modify my picture here to represent that lens. So in your lens diagram, this is how we represent a lens with a negative focal length. Okay. Just reverse the arrow directions, they point inward. Now, ray diagrams would basically do the same thing. And I always start with that parallel ray. A ray that leaves that tip parallel. Do those in blue again. It's such a nice color to look at. Whoops, that's not blue. A ray that leaves parallel. Now, the diverging lens is designed to, just like its name implies, make those rays leave, and it directs them away from the focal point. So this ray is going to be reflected like so, and basically just go off into space like that. Next principal ray. A ray that goes through the center of the lens just keeps on going. Again, that's because the center of the lens is basically vertical at that point. enough. Now, first thing to realize is these rays never cross over on the right, so the image is not formed over on the right. The image is going to be formed over on the left somewhere. And now the third principal ray, I think is this. Let's see, it's the inverse of this one. So going away from the focal point parallel, inverse of that is going to be this. A ray heading towards this focal point will be refracted and come out parallel. Now, the image is formed where the perception of these rays intersects. Let me talk about by perception what I mean by that. So when we look at this parallel ray, looking from this viewpoint, like looking from over here, this ray appears like it came from back here somewhere. So I'm going to go ahead and draw that in a dashed line. I'm going to do the same thing for all of these. This ray appears to have come from somewhere off in this direction. And then the third one also appears to have come from this point. So the intersection point of all of these rays, and again, it's not a perfect picture, they're not intersecting perfectly, and that's because I didn't measure these out perfectly, but the intersection is approximately right here. There's our image. So again, when I talk about intersection point, these two rays are intersecting like there, and the other two I know are intersecting like there. They're pretty darn close to the same spot. And again, had I measured these distances out with a ruler before I did this, these all would be intersecting right at one point right there. I'm going to go ahead and put that red dot for the intersection point. All right. So before we actually work the problem here, what I'd like to do is just chat a little bit about expectations, because that's how you know when you're right or wrong, or at least how you have a good idea, is you check your results against expected or known values. So the first thing to realize is this is a virtual image. What makes it virtual is these are backtracked rays. They're not actually there. This ray is not actually here. It's up here. So this is really just an optical illusion. This thing doesn't actually exist, right? It's the image, you can see it from over here, but again, that image is basically an optical illusion. So this is an example of a virtual image. Virtual images are indicated in the equations by a negative value for the image distance q. So I'm expecting a value of q of negative, let's see, this is 15, maybe around negative 10. This image is upright, therefore the magnification should come out positive. And it looks like it's roughly a third the length of the original. So if I had to guess at it, the magnification here, based on my picture, maybe right around minus 0.3. So let's see how that works out. So a thin lens equation, 1 over p plus 1 over q equals 1 over f. In this example, the object distance is still 30 centimeters, positive, because it's a real object. The image distance we don't know. The focal length now is negative 15 centimeters, right? Converging lenses have positive focal lengths. Diverging lenses have negative focal lengths. So I'm going to now turn this over to my crew here and ask that they calculate a value for q. Negative 10. Negative 10 centimeters. All right, and that was right around my expectation. All right, magnification. Minus q over p, that's going to be minus 10 centimeters over p, which was 30 centimeters, and we get what, positive 0.3 out of that. And I think that's probably pretty close to what my expectation was for this problem. So again, the purpose of this video is just to kind of demonstrate how to work lens problems with just single lenses, whether it's whether it's a converging or diverging lens. This video, hopefully you've seen examples that represent a real image, and here's an example of a virtual image. And here's 2 examples of how to do the ray diagrams. Hope this video helps with these concepts. Have a great day.